Hello guys, welcome again. Today I'm going to be tackling this room, cryptographic basics. I'm still trying to just complete as many of these modules as I can of the cybersecurity 101 path, right? So let's get to it. Introduction. Oh, okay, all good. Yeah. Have you ever wondered how to prevent third parties from reading your messages? How can your app or web browser build a secure channel with a remote server? By secure, we mean that no one can read or alter the exchange data. Furthermore, we can be confident that we are connecting with the real server. Thanks to cryptography, these requirements are satisfied. Cryptography lays the foundation for our digital world. While networking protocols made it possible for devices spread across the globe to communicate, cryptography has made it possible to trust this communication. This room is the first of three introductory rooms about cryptography. There are no learning prerequisites except basic abilities to use Linux command line. If you're not sure, please consider joining the pre-security path. Learning objectives. Upon completion this room, you will learn the following: cryptographic key terms, importance of cryptography, Caesar cipher, standard symmetric ciphers, common asymmetric ciphers, basic mathematics commonly used in cryptography. Okay, next. Cryptography's ultimate purpose is to ensure secure communication in the presence of adversaries. The term secure includes confidentiality and integrity of the communicated data. Cryptography can be defined as a practice and study of techniques for secure communication and data protection where we expect the presence of adversaries and third parties. In other words, these adversaries should not be able to disclose or alter the contents of the messages, right? Cryptography is used to protect confidentiality, integrity, and authenticity. In this age, you use cryptography daily, and you're almost certainly, reading this over an encrypted connection. Consider the following scenarios where you would use cryptography. When you log in to TryHackMe, your credentials are encrypted and sent to the server so that no one can retrieve them by snooping on your connection. When you connect over SSH, your SSH client and the server establish an encrypted tunnel, right? So no one can eavesdrop on your session. When you conduct online banking, your browser checks the remote server certificate to confirm that you're communicating with your bank server and not an attacker's. When you download the file, how do you check if it was downloaded correctly? Cryptography provides a solution through hash functions to confirm that your file is identical to the original one. As you can see, you rarely have to interact directly with cryptography, but its solutions and implications are everywhere in the digital world. Consider the case where a company wants to handle credit card information and process related transactions. When handling credit cards, the company must follow and enforce the Payment Card Industry Data Security Standard, PCI DSS. In this case, this standard ensures a minimum level of security to store, process, and transmit data related to credit cards. If you check the PCI DSS for large organizations, you will learn that the data should be encrypted both while being stored at rest and while being transmitted in motion. In the same way, the handling payment card details requires complying with PCI DSS. Handling medical records requires complying with their respective standards. Unlike credit cards, the standards for handling medical records vary from one country to another. Example laws and regulations that should be considered when handling medical records include HIPAA, Health Insurance Portability and Accountability Act, and the HITAC. Okay. Health Information Technology for Economic and Clinical Health in the USA, GDPR, General Data Protection Regulation in the EU, DPA Data Protection Act in the UK. Although the list is not exhaustive, it gives an idea about the legal requirements that healthcare providers should consider depending on their country. These laws are regulations and regulations show that cryptography is a necessity that should be present yet usually hidden from direct user access. What is the standard required for handling credit card information? PCI DSS. On to the next, plaintext for ciphertext. Let's start with an illustration before introducing the key terms. We begin with the plaintext that we want to encrypt. The plaintext is the readable data. It can be anything from a simple hello, a cat photo, credit card information, or medical health records. From a cryptography perspective, these are all plaintext messages waiting to be encrypted. The plaintext is passed through the encryption function along with the proper key. The encryption function returns a ciphertext. The encryption function is part of the cipher. A cipher is an algorithm to convert the plaintext into a ciphertext and vice versa. To recover the plaintext, we must pass the ciphertext along with the proper. Okay, let's check the graphic first. Sender plaintext, yeah. Then you encrypt it, and then you get the ciphertext. You encrypt it with the key, right? To recover the plaintext, we must pass the ciphertext along with the proper key via the description function, which would give us the original plaintext. This is shown in the illustration below. Ciphertext, so we decrypt it with the key, and then we get the plaintext again. Right? We have just introduced several new terms, and we need to learn them to understand. We need to learn them to understand any text about cryptography. The terms are listed below. Plaintext is the original readable message or data before it's encrypted. It can be a document, an image, a multimedia file, or any other binary data. Ciphertext is the scrambled, unreadable version of the message after encryption. Ideally, we cannot get any information about the original plaintext except its approximate size. Cipher is an algorithm or method to convert plaintext into ciphertext and back again. A cipher is usually developed by a mathematician. Key is a string of bits the cipher uses to encrypt or decrypt data. In general, the used cipher is public knowledge. However, the key must remain secret unless it is the public key in asymmetric encryption. We will visit asymmetric encryption in a later task. Encryption is the process of converting plaintext into ciphertext using a cipher and a key. Unlike the key, the choice of the cipher is disclosed. Decryption is the reverse process of encryption, converting ciphertext back into plaintext using a cipher and a key. Although the cipher would be public knowledge, recovering the plaintext with the knowledge of the key should be impossible, infeasible. Okay, what do you call the encrypted plaintext? I guess ciphertext. And what do you call the process that returns the plaintext? That's decryption. Yeah, historical ciphers. Cryptography's history is long and dates back to ancient Egypt. Okay. However, one of the simplest historical ciphers is the Caesar cipher from the 1st century before Christ. The idea is simple. Wait up. Before the Common Era, not before Christ. Yeah, I had to look that up. Before the Christian era is also, yeah, right. Simple shift. Oh, I'm sorry. What was I? The idea is simple. Shift each letter by a certain number to encrypt the message. Consider the following example. Plaintext TryHackMe. I've read about this before, so I'm gonna just skim through it fast, right, guys? Because I'm going through these concepts, but I already know many of them, right? So because I've read modules from TryHackMe before, and I've already read about cryptography, and yeah, basically these are okay that move the letter three times so that they could communicate in a safe manner, right? So 3, assuming it has a right shift of 3, we're going to figure out that T becomes W, R becomes and so on. So you notice once we reach Z, we start all over as shown in the figure below. We can see we get the ciphertext as, yeah, to decrypt we need the following information. Ciphertext, key 3, yeah, okay. For encryption, we shift for the right by 3. For decryption, we shift to the left by 3 and recover the original plaintext as illustrated in the image below. However, if someone gives you a ciphertext and tells you that it was encrypted using Caesar cipher, recovering the original text would be trivial task as there are only 25 possible keys. The English alphabet is 26 letters, and shifting by 26 will keep the letter unchanged. Hence, 25 valid keys for encryption with Caesar cipher. The figure below shows how decryption will succeed by attempting all the possible keys. In this case, we recover the original message with key equal to 5, consequently by today's standards, where the cipher is publicly known. Caesar cipher is considered insecure, of course. You would come across many more historical ciphers in movies and cryptography books. Examples include the Beguinier cipher from the 16th century, the Enigma machine from World War II, and the one-time pad from the Cold War. Knowing that it was encrypted using Caesar cipher, what is the original plaintext? You know what? That's why I have Grok. So by 3, results in what? Okay, Grok's taking its time. No, you can do something too. Okay, Grok didn't give me the answer. That's weird. Should be easy. What? That's weird. Actually, Grok just showed me how it basically used the 1 to 25 to decode. That was encrypted using Caesar cipher. What is the original plaintext? Uh-huh. Uh-huh. Okay, so what if I just go to ciphertext? So this one goes from, what am I even doing here? Decode. I'm not even sure. Is that it? Nope. I'm not sure. Decode scissor cipher. Check this one out real quick. Come on. I don't want to take too long on this. Caesar cipher, this is the text. The crypt root force, decode Caesar cipher. What do we have? What do we get? Number, shift key number using English alphabet. Yeah. Decode Caesar. Is that it? Nope. What? Yeah, there's like, there must be a problem with this, guys. What is the original plaintext? Mm-hmm. I'm actually trying all of them because I want to get done with this exercise, but none of them are working. Which one makes sense? Get the ABCC? I don't know. Rotation by 10. Mm-hmm. None of them. Yeah, what? I don't know. I'm gonna Google this real quick, guys, because I don't know what the heck. Mm-hmm. I can encrypt. I can encrypt. But there's just no... there's no I can encrypt here, guys. Oh, I got it. Is this the one? Brute force, untested and sorted from most probable to least probable. Oh, okay, what's this one? Greg couldn't do it. How would you... Grok, I'm sorry. How would you get to this? The terminal you can encrypt would be encrypted from using a Caesar cipher. Count the shifts. We need to find shift value. 15 for us, or both wrapping around the alpha, so let's confirm. So indeed, I can encrypt with a shift of 15 to the right results in. Then why did you not? So did you not try to the right? Oh yeah, okay. Okay, well anyway, let's get on. Types of encryption. The two main categories of encryption are symmetric and asymmetric. Symmetric encryption. Symmetric encryption, also known as symmetric cryptography, uses the same key to encrypt and decrypt the data. Shown in the figure below, keeping the key secret is a must. It is also called private key cryptography. Furthermore, communicating the key to the intended parties can be challenging as it requires a secure communication channel. Maintaining the secrecy of the key can be a significant challenge, especially if there are many recipients. The problem becomes more severe in the presence of a powerful adversary. Consider the threat of industrial espionage, for instance. Consider the simple case where you created a password-protected document to share. To share with your colleague. You can easily email the encrypted document to your colleague, but most likely you cannot email them the password. The reason is that anyone with access to the mailbox would access both the password-protected document and its password. Therefore, you need to think of a different way, channel to share the password. Unless you think of a secure, accessible channel, one solution would be to meet in person and communicate the password to them. Examples of symmetric encryption are DES, Data Encryption Standard, 3DES, triple Ds, And AES, Advanced Encryption Standard. Okay, it was adopted to a standard in 1977 and uses a 56-bit key. With advancements in computing power, in 1999, a DES key was successfully broken in less than 24 hours, motivating the shift to 3DES. Applied 3 times consecutively, the key size is 168 bits, though the effective security is 112 bits. 3DS was more of an ad hoc solution when DES was no longer considered secure. 3DS was deprecated in 2019 and should be replaced by AES, however, it may still be found in some legacy systems. AES was adopted as standard in 2001. Its key size can be up to 256 bits. There are many more symmetric encryption ciphers used in various applications, however, they have not been adopted as standards. Asymmetrical encryption. Unlike symmetric encryption, which uses the same key for encryption and decryption, asymmetric encryption uses a pair of keys, one to encrypt and the other to decrypt. As shown in the illustration below, to protect confidentiality, asymmetric encryption or asymmetric cryptography encrypts the data using the public key, hence it is also called public key cryptography. Examples are okay. Examples are RSA, Diffie-Hellman, and elliptic curve cryptography. The two keys involved in the process are referred to as public and private key. Data encrypted with the public key can be decrypted with the private key. Your private key needs to be kept private, hence the name. Asymmetric encryption tends to be slower, and many asymmetric encryption ciphers use larger keys than symmetric encryption. For example, RSA uses 2048 bit. Okay, keys 2048 bit is a recommended minimum key size. Diffie-Hellman also has recommended minimum key size up to 4096 bit keys for enhanced security. On the other hand, ECC can achieve equivalent security with shorter keys. For example, with a 256 bit key, ECC provides a level of security compared to 3072 bit RSA key. Asymmetric encryption is based on a particular group of mathematical problems that are easy to compute in one direction but extremely difficult to reverse. In this context, extremely difficult means practically unfeasible. For example, if we can rely on mathematical problem that would take very long time, for example, millions of years to solve using today's technology. We'll visit various asymmetric encryption ciphers in the next round. For now, the important thing to note is that asymmetric encryption provides you with a public key that you share with everyone and a private key that you keep guarded and secret. Summary of new terms. Alice and Bob are fictional characters commonly used in cryptography examples to represent two parties trying to communicate securely. Symmetric encryption is a method in which the same key is used for both encryption and decryption. Consequently, this key must remain secure and never be disclosed to anyone except the intended party. Asymmetric encryption is a method that uses two different keys, a public key and a private key for decryption. Should you trust DES? Nay. When was AES adopted as an encryption standard? If I remember correctly, it was 2007 or 2001, or maybe I got this all wrong. Yeah, 2001. Basic math. The building blocks of modern cryptography lie in mathematics. To demonstrate some basic algorithms, we'll cover two mathematical operations that are used in various algorithms: SOR operation and modulo operation. Okay, SOR, short for exclusive OR, is a logical operation in binary arithmetic that plays a crucial role in various computing and cryptographic applications. In binary, XOR compares two bits and returns one if the bits are different and zero if they are the same. As shown in the truth table below, this operation is often represented by the symbol this symbol or this other symbol. Okay, 0, 0, 0, 1, 1, 0. Okay, if this is the first time you work with the truth table, it is a table that shows all possible outcomes. The XOR truth table above states all 4 cases. Let's consider an example where we want to apply XOR to the binary numbers. In this case, we perform the operation bit by bit. 1 with 1, 0 with 1, and then okay, resulting in 0, 1, 1, 0. You may be wondering how XOR can play a role in cryptography. XOR has several interesting properties that make it useful in cryptography and error detection. One key property is that applying XOR to a value with itself results in 0, and applying XOR to any value with 0 leaves it unchanged. This means A equals 0 and A is 0, A for any binary value. Additionally, XOR is commutative, A, and it's associative. Okay, let's see how we can make use of the above in cryptography. We'll demonstrate how XOR can be used as a basic symmetric encryption algorithm. Consider the binary values P and K, where P is the plaintext and K is the secret key. The ciphertext is C. Okay, now, if we know C and K, we can recover P. We start with CK, yeah, equals PK. K, okay. But we know that PK, okay. Because SOR is associative. Furthermore, we know that K is 0. Consequently, P okay equals Okay, so in other words, or serve the simple symmetric encryption algorithm. In practice, it is more complicated as we need the secret key as long as the plaintext. And the modulo operation. Another mathematical operation we often encounter in cryptography is the modulo operator, commonly written as a percentage or a small. The modulo operator is the remainder when x divided by y. In our daily life calculations, we focus more on the result of division than on the remainder. The remainder plays a significant role in cryptography. You need to work with large numbers when solving some cryptography exercises. If your calculator fails, we suggest using a programming language such as Python. Python has a built-in int type that can handle integers or arbitrary size and would automatically switch to larger types as needed. Many other programming languages have dedicated libraries for big integers. If you prefer to do your math online, consider Wolfram Alpha. Okay, let's consider a few examples. 25 module 5 0, 23 6 would be 5. 2372. The important thing to remember about model is that it's not reversible. If we're given the equation x for and infinite values of x would satisfy this equation, the modulo operation always returns a non-negative result less than the divisor. This means that for any integer a and positive integer n, the result of a mod n will always be in the range of 0 to n minus 1. What's so this would be 1 with 1, what is it? 0, 0 with 0 is 0. And then 0 with 1 is 1. And then 1 with 0 is 1 as well. Yeah, what is, okay. Let's ask Grok. Let's compute now, subtract 4, 6, 65. Well, that can be it. What the heck? Is Grok really failing me this bad? I'm gonna ask ChatGPT. ChatGPT just gave me the response straight up, 3565. And then what's, oh well, this is 0, come on. Summary. In this room we learned about the importance of cryptography and some of the problems that it solved. We also introduced symmetric and asymmetric encryption ciphers. Finally, we explained the XOR and the modulo operations. In the next room, public key cryptography will visit various asymmetric crypto systems and see how they solve the problems we face in the digital world. Before proceeding to the next room, make sure you have taken note of all the key terms and concepts introduced in this room. Yeah, sure. Alright guys, this is it for this module, Cryptography Basics. We'll be moving on to the next one. Thanks for sticking up with me. Hopefully we learned something together here. Yep. Bye guys. Peace.